basic communication principles, and we continue with the communication basics, and we will now look at digital modulation schemes. We have earlier in this course we have looked at digital signaling, where for example we have two voltages, 0 volts and 5 volts for example, representing a binary low and a binary high, binary 0 and binary 1. Well, that is not very easy to send, for example, on a wireless transmission line, where you would rather send no signal and then a wave when you have a logical 1. So that would be amplitude shift keying, or you can even have a low amplitude meaning 0 and a high amplitude meaning 1. That is amplitude shift keying. Another possible way to communicate is by using FSK, frequency shift keying, where you have low frequencies for low bits and high frequencies for high bits. The benefit with that is that you can easily tell if you have lost your signal. There is no signaling in the amplitude itself. So therefore it's more robust when it comes to noise. Then you have something called phase shift keying. Look at this. You have a phase shift when there is a 1 coming. Phase shift means that there's a 1 coming. A phase shift, there's a 1 coming. And no phase shift here, so that's because there's a 0 coming. Phase shift, there's a 1 coming. The benefit with that one is the same as the FSK, but you also use fewer frequencies. You see, all the signals here have the same frequency, so it's easier to put different channels close to each other. You may also have a set of states called symbols. So each of these are a symbol. So one symbol here and one symbol here. Here is one symbol and here is one symbol. But you may also have, for example, if you have 1-bit communication, you need 2 different symbols. But you can communicate 2 bits at a time by using 4 different symbols. So let's look at that. If we have the 4 possible bits, those are the 4 possible combinations of 2 bits. So let's say that in this 0,0 case, I have low amplitude and low frequency. In this case, I have high amplitude and low frequency. In this case, I have low amplitude, so this one controls the amplitude, and this one controls the frequency. So I have high frequency, low amplitude. And in this case, I have high frequency and high amplitude. So by doing that, for each symbol I send, I really send 2 bits. So I can analyze if I have low frequency. Yeah, I know that this one, the bit here, is one of the 2 here. And if I have low amplitude as well, I know it's one of these 2. So therefore, one symbol communicates 2 bits. And I can do even more. One symbol can have 4 bits, which means that I need 16 different symbols to carry 4 bits. Baud is in telecommunication. Baud is the number of symbols per second, while the bit rate is the number of bits per second. And we just learned that there might be a difference between symbols and bits, because each symbol can carry more than 1 bit. So, for example, if I have a computer here, and I have a computer here, and I have some equipment between them in order to send a message from A to B. So if this is me and this is you, if I'm sending data from me to you, I, as a user, I'm really interested in the bit rate. How many bits per second can I send? How fast can I send my email, for example? While the designers of the communication equipment in between here, they are more interested in the baud rate. How many symbols is this line capable of transmitting per second? So the baud rate is the number of symbols per second, while the bit rate is what the end user is interested in. So, but this is how many symbol, or actually symbol changes, can some device along the line tolerate. It can be a device or it can be a line. Anyways, they will be specified according to the number of symbol changes per second, which is the baud rate, named after Jean-Maurice Émile Baudot. So here we have one example here. In this case, we have 2 bits, 0 and 1, each represented by low frequency, high frequency, low frequency, high frequency. So each symbol carries 1 bit. So the bit rate is let's say that this communication with 6 bits takes 1 millisecond, 6 milliseconds, 6 bits, 6 milliseconds, so it's 1 kilobits per second. The baud rates, 6 different symbols during 6 milliseconds, so 1 kilobaud. In this case, I have 2 bits per symbol, low frequency, low amplitude, low frequency, high amplitude, low amplitude, high frequency, back to low amplitude, low frequency, high amplitude, high frequency, and so on. So each symbol here will carry 2 bits. So I was able to send 12 bits during the same 6 milliseconds. Therefore, my bit rate is 2 kilobits per second, while the number of bauds or number of symbols per second was 6 symbols, 6 milliseconds, 1 kilobaud. So my equipment was able to change the symbol 1000 times per second, while I received 2000 bits per second. We also have other examples like the QAM, which is a standard, where you have 16 different symbols where you vary with amplitude and phase. So to form 16 different symbols. You may also see that there are symbol spaces here which are not used, and that is because you want to have a bit of a difference between the different symbols. You are not supposed to study this in detail, but it's just an example where you have 4 bits per symbol. So here the bit rate would be 4 times the baud rate. The baud rate is always lower or equal to the bit rate.